In this video, our topic for discussion is iteration methods of solution of system of linear equations, in which we discuss Gauss-Jacobi, Gauss-Seidel and relaxation methods. So these three are the prominent iteration methods for solving a system of linear equations. You know many methods for solving system of linear equations like elimination method, matrix inversion, determinant, rank method, etc. and few more methods. But the main drawback of those methods are they are not suitable a system containing a large number of unknowns and a large number of equations. They are not recommended when you want to solve a system with large number of equations in large number of unknowns. That's why these iteration methods come to help. Here we shall discuss only Gauss-Jacobi, Gauss-Seidel and relaxation methods. These are iteration methods. So let's discuss these methods. To find the solution of a system of n linear equations in n unknowns x1, x2 up to xn of the form. So this is the system of linear equations where we have n equations and n unknowns. And one more thing, these are special types of systems in which we have the absolute value of a11 larger than a12 up to a1n. So this absolute value of a11 must be larger than the absolute values of all other coefficients in the equation. Similarly, a22 must be larger than all the other coefficients in this second equation, and so on. Such systems are called diagonally dominant system. In such systems, we have largest elements on diagonal, and such systems are called diagonally dominant systems. So these methods are suitable for diagonal dominant systems. For other systems, the method may or may not work or may require a large number of iterations. This is the compact form of this system. For each I, this diagonal element aii is larger than other elements aij in that particular row. These methods are suitable only for diagonally dominant systems. So let's discuss the first method, which is Gauss-Jacobi's method. In Gauss-Jacobi's method, we find the values of unknowns x1, x2 up to xn in successive steps using these formulae. Using the first equation of the diagonal dominant system, we write value of x1 as 1 upon a11 and all other variables are shifted on the right. Similarly, x2 is obtained using the second equation of the diagonal dominant system and all other variables are shifted on right, and so on. x1k plus 1 is showing the new value of x1 at each iteration. Similarly, x2k plus 1 is the new value of x2 at each iteration, and so on. And here on the right we see x2k, x3k, x4k up to so on. So these are the old values of x2, x3 up to xn. So on right hand side we have old values of x, x1, x2, x3 up to xn, that means old values of unknowns, and on the left side we have new values of the unknowns. So at each step we find a set of new values of unknowns and use them in the next step. Each iteration we find the new values of the unknowns x1, x2 up to xn using the old values and then use them in the next iteration. And this process will go on up to desired accuracy. That means until we get the desired values of x1, x2 up to xn. The set of values of x1, x2 up to xn we get in the last iteration will be the solution of the system. So here we start with x1, x2 up to xn equal to 0 and find x1, x2 up to xn in successive steps in Gauss-Jacobi iteration method. Like so, we shall take an example to demonstrate this method. So look at this example. In this example, we are asked to find the solution of the system of equations using Gauss-Jacobi's method using 8 iterations. So here we have to perform 8 iterations. So look at this example. Now in this system, we have to use Gauss-Jacobi's method to find values of x, y and z satisfying all these equations simultaneously. So first of all, we look at the system of equations and we find that the largest coefficient of x is in the second equation. So numerically largest coefficient of x is in the second equation and largest coefficient of y is in the first equation and the largest coefficient of z is in the third equation. So numerically largest coefficients of x, y, z are 7, 9 and minus 12 respectively. So we have to write the equations using partial pivoting. So using partial pivoting, we put the second equation at the first place because it has the largest coefficient of x. Then in the second place we put the equation first equation because it has the largest coefficient of y, and in the third place we put the third equation because it is numerically largest coefficient of z. So using partial pivoting, we have to arrange the equations like this so that it is now diagonal dominant. You can see the elements on diagonal the largest as compared to other coefficients. So now we have a diagonal dominant system. So we can start this method, Gauss-Jacobi's method. So using Gauss-Jacobi's method, iteration method, we find the formula for x, y and z. So using the first equation, we find value of x as 5 plus 2y minus z. So this is the new value of x and these are the old values of y, z. So using old values of y, z, we find new value of x. Similarly for y, we have this equation. So we have formula for x, y and z using Gauss-Jacobi's iteration. And on RHS, we have old values of x, y, z. And on LHS, we have new values of x, y and z. Now we start with 0, 0, 0. So initially we have to start with x equal to 0, y equal to 0, z equal to 0. So these are initial iteration. So we have to write like this: x0, y0, z0. So initially or starting is from 0, 0, 0. So we have to prepare the table like this. These are the columns. These are the old values of x, y, z, and these are the new values of x, y, z. K equal to 0. We have x0, y0, z0, which are 0, and using y and z in the first equation. So what is x1? X1 is 5 plus 2 into y0. Y0 is 0 minus 0. Z is also 0 divided by 7. So this is equal to 0.7143. So this is x1. Similarly for y1, again we have minus 1 by 9, and similarly for z1 we have minus 2 by 12. That means 1 by 6. So these are the new values of x, y, z. That means x1, y1, z1 using the old values x0, y0, z0. So these are the entries, new values. Now using these values in the next iteration. So we have to copy all these values here. So these are x1, y1, z1, and using these x1, y1, z1 we find x2, y2, z2. So here x2 will be 5 plus 2 into, what is x1? X1 is y1 minus 0.1111 minus z, that means minus 1667 minus 0.1667 divided by 7. So this comes out as 0.7063. Similarly y2 we have to find from here 1 plus 3 into x, 0.7143 minus 4 into z. Z is minus 0.1667 divided by 9. So this comes out as 0.2011 and so on. Similarly z2 we can find using x and y, new values of x and y. New values of x and y. So z comes out as 0.1177. So these are the new values of x, y and z. So these are x2, y2, z. Again copy these x2, y2, z2 in the next iteration and we find new values of x, y, z, x3, y3, z3. So all these values, new values are copied down here in the next step and they are used to find the new values of x, y, z using this formula. So proceeding in this manner, we find that up to 8 iterations, we find that the value of x is this 0.7457, value of y is 0.1229 and value of z is 0.0292. So we are asked to find the solution by performing 8 iterations. So after this 8th iteration, we stop here and we write the solution as x equal to 0.7457, y equal to 0.1229 and z equal to 0.0292. So this is the approximate solution of this system. Practically, when you are not asked to perform a specific number of iterations, then you have to perform until you get the solution. So what is the stopping criteria? The stopping criteria is you look at the values of x, y and z in these columns, and if you find that these values are constants up to desired places of decimal, then you should stop. For example, if you are asked to find these values up to 3 places of decimal, then you should stop whenever you get all 3 x, y and z correct to 3 places of decimals. That means if they repeat up to 3 places of decimal, then you should stop. So by looking at the values of x, y, z, you decide where to stop. So if you perform more iterations 9, 10, 11, 12, then you will find that x will be stable up to 3 or 4 places of decimal. Similarly, y will be stable up to 3 or 4 places of decimal, and z is stable up to 3 or more places of decimal. So there you should stop and write the solution whenever you get the repeating values of x, y and z respectively, you should terminate the method or you have to stop there. So this is Gauss-Jacobi's iteration method. Next method is Gauss-Seidel iteration method. This method is better than the Gauss-Jacobi's method because the number of steps required is generally half of that required in Gauss-Jacobi's method. So let's discuss what is this method. To find the solution of the system using Gauss-Seidel iteration method, we write the formula for the unknowns x1, x2 up to xn using the diagonally dominant system. So first equation is used for finding values of x1. Second equation is used for x2 and so on. So as usual, we write these formulae. Now what is the difference between these formulae and those used in Gauss-Jacobi's method? We start from x1, x2, x3 up to xn equal to 0, and then using the first equation we find x1. So new value of x1 is obtained using old values of x2, x3 up to xn as usual, as we do in Jacobi's method. But while finding x2, new value of x2, the change is here we use this x1 immediately. So this is the main difference between Gauss-Jacobi's and Gauss-Seidel method, that here we use new value of x1 to find new value of x2 immediately. And values of x3, x4 up to xn are the old values because at this stage there is no new values of x3, x4 up to xn. Similarly, when we find new value of x3, we use both x1 and x2 in x3. So here x1 and then this x2 and so on. In this way, the new values obtained are used in finding new values of other unknowns. This is the main difference between Gauss-Jacobi's and Gauss-Seidel iteration methods. Take an example. Solve the following system of equations using Gauss-Seidel iteration method. So again, we take the same example as we have taken in Gauss-Jacobi's method. So look at this example. So after partial pivoting, we get this system of equation where it is diagonally dominant. The values at diagonal are larger than other coefficients. So using Gauss-Seidel iteration method, we form the formulae. So here the first equation is used to find values of x. So we write xk plus 1 equal to 5 plus 2yk minus zk upon 7. So this is by first equation. Now using second equation, we find value of y, which is this, minus 1 plus 3yk plus 1 minus 4zk upon 9. So here the value of xk is available, new value of xk is available, so we use here new value of xk. But in Gauss-Jacobi's method, here we use the old value of xk. So this is the main difference. Here at this stage we have xk plus 1 available, so we use here xk plus 1. And to find new value of z, we use both xk plus 1 and yk plus 1, because xk plus 1 and yk plus 1 are available when we find zk plus 1. So these are the formulae for x, y and z in Gauss-Seidel iteration method. Now starting from 0, 0, 0, the new values are shown in the table. So this is the new value. So starting from 0, 0, 0, the new values of x, y and z are 0.7143, 0.1270 and 0.0185. Now this value of x is obtained using this formula. So x1 is 5 by 7 because y equal to 0, z equal to 0. So this is 0.7143. New value of y is obtained using this formula. But while using this formula, we have to use new value of x, which is available 7143. But new value of z is not available, so z equal to 0. So here it is 0 upon 9. So this value comes out as 1270. Similarly, z, new value of z is using this formula minus, this is 2 minus 4 into. Now what is the new value of x, which is 0.7143. So you have to use these two new values to find z. Then plus 5 into y, 0.127, new value of y divided by 12. So this comes out as 185. So these are the values of new values of x, y and z using Gauss-Seidel iteration method. Now you copy all these values here in the second iteration. So for k equal to 1, we have this x1, y1, z1, and this new value of x2 is obtained using these two values of y and z. So this is 5 plus 2 into 0.1270 minus 0.0185 divided by 7. This is the new value of x, 0.7479. Similarly, new value of y is obtained using this formula. So minus 1 plus 3 into. Now what is the new value of x? The new value of x which is available at this stage is 0.7479. 7479. Then minus 4 into z. New value of z is not available. So at this stage the value of z available is 0.0185 divided by 9. So this comes out as 0.1300. Similarly, the new value of z is minus 2 minus 4 into. The new value of x available at this stage is 0.7479 minus plus 5 into new value of y which is available at this stage is 0.1300 divided by 12, which comes out as 0.0285. So in this way you find new values of x, y and z using the values in the same step. So here to find y we have to use this new value of x. To find z we have to use these two values of x and y. So at every step we have to use Gauss-Seidel iteration method like this. We have to use the new values of the unknown as soon as it is available to find the new value of another unknown. So proceeding in this manner, we find that values of all x, y and z are repeating. So we find that in the fifth step we get the solution. So we see that here values of x are stable up to 4 places of decimal. Similarly, values of y are stable at up to 4 places of decimal and values of z are stable. So these values are stable now. So if we repeat this method more number of times, then we find that the solution will not change. This is the solution. So here we see that we obtain the solution in the fifth step in Gauss-Seidel iteration method, but the same solution was obtained in Gauss-Jacobi's method in almost 11 or 12 steps. Therefore, this method is better than the Gauss-Jacobi's method. It reduces the labor. The number of steps required is generally half of that required in Gauss-Jacobi's method. Therefore, this method is better. Another iteration method is relaxation method. So in relaxation method, again, we start with a diagonal dominant system. So here we are using this notation, compact notation, because this method requires this notation. So again, this is diagonal dominant system. So here we find Ri equal to Bi minus summation Aij xj. That means using the first equation, we write R1 as B1 minus A11 x1 minus A12 x2 up to minus A1 and xn. And this is called the residual or the first residual. Similarly, second residual is obtained using second equation A21 x1, A22 x2 up to A2 and xn and so on. So in this way we find n residuals using those equations an1 x1 minus an2 x2 minus an xn. These Ri's are called the residuals, and the solution of this system is obtained when each residual is 0. So when R1, R2 up to Rn equal to 0, then we obtain the solution of this system of equations. Therefore, our aim is to reduce these residuals to 0 in successive steps. So again, starting from 0, 0, 0, we reduce each residual to 0 in successive steps. And to reduce the residual to 0, at every step, we reduce the largest residual in magnitude to 0. So we select the largest residual in magnitude and make it 0 or reduce it to 0. So how to do it, I will explain through an example. To reduce this ith residual to 0, we give increment to ith variable. So we have to give increment to ith variable, which is determined by this formula Ri upon Aii. So dxi equal to Ri upon Aii with minus sign. This is the increment we give in ith variable. That means in the next step, ith variable becomes xi plus dxi and all other variables remain as they are. So there is a change in the value of xi at each step. There is change in value of xi if Ri is the largest residual in magnitude. So we change only xi and keep all other unknowns as they are. So in this way we reduce the ith residual at each step using this formula. So we give increment to only that unknown for which the residual is largest in magnitude. So let's take an example. Take the same example. So using partial pivoting, we write this system of equation as. Then the residuals. So first residual Rx is by using first equation 5 minus 7x plus 2y minus z. Second residual Ry equal to minus 1 plus 3x minus 9y minus 4z. And third residual Rz is 2 minus 4x plus 5y plus 12z. So these are the residuals. So our purpose is to make all the residuals equal to 0. So we have to find those values of x, y, z for which Rx, Ry, Rz equal to 0. So how to start? The operational table is this table. If you find that Rx is the residual which is largest in magnitude, then increment in x will be given using this formula. If Ry is the largest residual in magnitude, then increment in y will be dy equal to minus Ry upon minus 9 and so on. So these are the increments given to x, y and z if the corresponding residuals are largest in magnitude. So starting with 0, 0, 0, the computations are given in the following table. So look at this. If we start with 0, 0, 0, x equal to 0, y equal to 0. So put x equal to 0, y equal to 0, z equal to 0 in each residuals. You find that Rx equal to 5, Ry equal to minus 1, Rz equal to 2. So largest residual in magnitude is 5. So we select this 5 and give increment in x. So this is the formula for increment. Here this is the formula for increment. So Rx equal to 5 upon minus 7 with minus sign. So if we solve this, we get 0.7143. So in the next step, x will become 0.7143. 0 plus, this is 0 plus 7143. And there is no increment in y and z. So they are as they are. So using this value, x equal to 0.7143, y equal to 0, z equal to 0, we again find the residuals. Again find the residuals using the same formula. And we find that this time Ry is the largest in magnitude. So Ry, we select Ry. And this time we have to give increment to y. So this is the formula for the increment. This increment or this amount should be given to y. So using this 0.1270, so 0 plus 0.1270, 0.1270. So we have to give increment to y and this will be as it is 7143 and also z will be as it is. There is no change in z. So these are the new values of x, y, z. So here increment is given to y only because here largest residual is corresponding to y. So this is the amount of increment which should be given to y. So amount of increment is 0.1270. So using these x, y, z in again Rx, Ry, Rz, we get these values of Rx, Ry, Rz. So largest magnitude is this 0.2540. So this time we have to give increment to x. So this is the amount of increment 0.0363. So here we have to give increment in the next step 0.363. So this is the increment we have to give in x, y as it is, z as it is. So these are the new values of x, y, z. And when we put x, y, z here again Rx, Ry, Rz, we obtain new values of Rx, Ry, Rz. And here we see that the largest magnitude is of Rz. So we give increment to z. So this is the amount of increment which will be given to z. So now z will be in the next step, z will be 0.0363 and x and y will be 1270 and z will be 0.7506. So these will be the new values. Increment will be given to z only. So in the next step, again using x, y, z, you find that Rx is the largest in magnitude and so on. So here we have to give increment to x only. So this is the amount of increment which will be given to x. So here we have to give 0.0044, 0.1270 as it is. Okay, this we have to add this as it is and this as it is 0.0306. So using this these values, we obtain Rx, Ry, Rz. Now this time Ry is largest in magnitude among these two. Therefore, the increment should be given in Y. So this is the amount of increment. So here we have to add 0.0030. So we have to add these two and keep X and Z as they are, 7462 and 0.306 and so on. So repeating this method until we get all residuals 0. So here we see that at 9th and 10th steps, values of X, Y, Z remain constants. They do not change and corresponding residuals are almost 0. Therefore, by looking at the residuals, they are almost 0 and there is no change in the values of X, Y, Z. So if we further repeat this method for 11 and 12, k equal to 11 and 12, we find that these values will not change. Therefore, values of Rx, Ry, Rz will not change. So ultimately, our solution is X equal to 0.7454, which is this, Y equal to 0.1240 and Z equal to 0.0301. So this is how you obtain solution using relaxation method. So I hope you understood what I have told you. Thank you very much.